Rational functions and end behavior. In this video, we're going to be looking at horizontal asymptotes, how to find them if they exist, and where they would be located. And all of it's going to come down to a comparison between the degree of the numerator and the degree of the denominator. For example, h of x, the degree of the numerator is going to be the highest exponent that we see, and that would be a 2. The degree of the denominator is also going to be 2. Okay, so in h of x, the degree of the numerator and the degree of the denominator are actually the same thing. And there's something that we'll be able to learn from that. For j of x, the degree of the numerator is going to be a 1. The denominator is a 4. Okay, so this is a second case where the degree of the denominator is greater than the degree of the numerator. The third case, which we don't have an example of yet, is going to be when the degree of the numerator is greater than the degree of the denominator. All right, for our first case, if the degree of the denominator is greater than the degree of the numerator, a horizontal asymptote will exist, and it will be the line y equals 0. In other words, it's going to be the x-axis. Okay, if the degree of the denominator is greater than the degree of the numerator, you will get a horizontal asymptote at the x-axis. For example, j of x was equal to 5x over x to the 4th. We have a comparison of a degree 1 to degree 4. Degree 4 is greater, the degree of the denominator is greater, so we're going to get a horizontal asymptote at the x-axis. All right, and since we haven't figured out all the aspects of graphing yet, what we're still going to do is use the calculator to get an idea of what this picture looks like. And that's the graph that we get. You can see that we do have a horizontal asymptote at the x-axis. Okay, you're also going to have a vertical asymptote at the y-axis. It appears to be over there, which should make sense because this function is going to be undefined for values of 0. Okay, that can either create holes or asymptotes. In this case, it actually does create an asymptote. All right, and to draw a picture of the graph, we're just going to do a basic sketch. Really, all we want to do is highlight the horizontal asymptote and the vertical asymptote. All right, our second case, if the degree of the numerator and the denominator are equal, a horizontal asymptote will exist, and it's going to be at a particular line. It's going to be at the line y equals a divided by b, where a and b are the leading coefficients of the numerator and the denominator. Okay, sounds like a lot, but it's actually really, really easy. Let's think back to h of x. H of x is equal to 8x squared plus 2 divided by 4x squared. The degree of the numerator is 2, the degree of the denominator is 2. Okay, they have the same size degree. So there is going to be a horizontal asymptote. It's going to be at y equals a over b, where a and b are the leading coefficients. In this case, that would be the 8 and the 4. Which is going to reduce to 2. So we have a horizontal asymptote at y equals 2. In addition to that, you're going to have a vertical asymptote at the y-axis because when x is 0, it becomes undefined. All right, so let's see what the calculator shows us as a graph. I've already got it typed in. There's that vertical asymptote at the y-axis. You're also going to see that it flattens out above the x-axis, which is actually going to be at y equals 2. In fact, I can add that to the graph just so that you can see it. Okay, go to y equals. We'll just type in 2. And there's that asymptote. It does appear that the graph may be contacting the asymptote, but it is not. They're just getting infinitely close to each other. All right, so a quick sketch of the graph. All right, so we have one more case to consider. What happens if the degree of the numerator is greater than the degree of the denominator? In this case, there's only one particular scenario that we're going to look at, and that'll be when the degree of the numerator is greater than the degree of the denominator by exactly 1 degree. So you're going to notice in k of x that the degree of the numerator is a 2, the degree of the denominator is a 1. We have a difference of 1 degree. Okay, now if the numerator has a degree that's much higher than the degree of the denominator, those will be cases that we don't look at. So this is one particular scenario that we're going to consider. And what we're going to go ahead and start with is just taking a look at the picture that we get from this as a graph, which looks like this. Okay, a different case, right? No horizontal asymptote. We actually don't have a horizontal asymptote. We do have a vertical asymptote, which appears to be right around here, and you can determine that that's actually going to be at 3. Okay, so let's go ahead and draw that. All right, but we don't have a horizontal asymptote. We do have something else going on, though. We have something happening over here and something happening over there. Okay, we're going to investigate that by actually dividing these two things. And because of the denominator that we have, we can actually divide by synthetic division. Okay, so let's set that up. We've got the box. If we're going to divide by x minus 3, we're going to put a 3 in the box. The coefficients of the numerator go here. And we start the process. We're going to drop the 1. 1 times 3 is 3. These together will give you -1. Multiply by 3, you get -3. Together, we get -7. Okay, so what does that represent? It represents x minus 1 with a remainder of -7. Okay, but what we're going to do is exclude the remainder. We're not going to think about that number. And now what I'm going to do is go back to the graph and graph this. And what we're going to get is a line that our graph appears to be approaching over here and over here. In other words, we are getting an asymptote, but our asymptote is not a horizontal asymptote. It's actually called a slant asymptote. And conveniently, the slant asymptote is the quotient of the numerator and the denominator when you exclude the remainder. All right, so let's go ahead and add that into the picture. We're going to have an intercept at -1. We're going to have a slope of 1. And our graph is going to exist in this area and this area. So quick sketch. And there we go. All right, so what I want to do now is summarize horizontal asymptotes and slant asymptotes as end behavior. Okay, end behavior describes the direction of the graph when the x values approach -infinity or infinity. In other words, as we go way out to the left or way out to the right, what happens at the ends of this graph? Okay, imagine substituting in a really large number for x. Okay, consider k of x, the last function that we looked at. If you were to substitute a very large number for x, there's certain terms that don't really matter anymore. Okay, when x becomes very large, the leading term of the polynomial is going to take precedence. Okay, just consider the top for right now. When you plug in really large values of x, you're going to have that value squared here. You're going to have it multiplied by -4, and then you're going to have this -4. Okay, so consider plugging in 1,000. If you were to plug in 1,000, 1,000 squared is going to be 1,000,000. Okay, and then this is going to be negative 4,000. Comparable, 1,000,000 is a lot bigger than 4,000. And it's definitely a lot bigger than minus 4. And as you choose larger and larger x values, the difference between the terms is going to become exaggerated. So ultimately, the leading term is really what's going to describe what happens in the polynomial. Same thing for the denominator. The larger value of x that you plug in, the more dominant it's going to become with respect to the other term. All right, so what we're going to do is eliminate all the terms other than the leading term, because ultimately, as x gets very large, whether very large positive or very large negative, those other terms are not going to be as important. Okay, so for k of x, what we can do is eliminate everything but the x squared and the x, which simply gives us x squared over x. But then we're going to reduce it. You're going to notice that both the top and the bottom have a factor of x. So it reduces to just x. And if you plug in a really, really large negative number, you get back a really, really large negative number. In other words, as you're moving to the left, that means to the left. As you're going to the left, your graph is going to go down. If you plug in a really large positive number, you're going to get back a really large positive number, which means that as you move to the right, the graph is going to go up. That'll be the end behavior of k of x, which we can confirm with the graph. It goes up to the right and it goes down to the left. For h of x, we can simplify it down to 8x squared over 4x squared. This will then reduce to 8 over 4 when you take out all the x's, but then that becomes 2. And you end up with a horizontal asymptote at 2. See, as you consider plugging in larger and larger x's, you don't actually have a place to plug them in. There isn't anywhere to plug it in. So it doesn't matter how big your x becomes. In the end, it's going to settle off at 2. Same thing in the negative direction. For j of x, we don't have any terms to eliminate, but we can reduce to 5 over 4x cubed. You can divide out an x from both sides. All right, so now consider plugging in really large values for x. When we do that, let's suppose we're plugging in a large positive number. When we do that, the denominator is going to continue to get larger and larger and larger. Okay, but the numerator is going to be stuck at 5. And if the numerator stays at 5 while the denominator continues to get larger, it's going to become 0. The same thing's going to happen when you plug in a really large negative number. Yes, it is going to be negative because it's cubed. It's going to maintain that negative. But the thing here is that the numerator stays constant. The denominator is getting larger and larger and larger, so it's still going to approach 0. It's just going to approach 0 from underneath the x-axis.
Later, blah.